Hello, this is Jack Jackson. In this section, we will review some of the basic concepts and formulas related to the distribution of proportions before we go on to talk about inferences about proportions. This material was covered back in Unit 2B, or the second half of the Unit 2 playlist here on YouTube, my YouTube channel. So let's go through this. So let's start by remembering that the distribution of proportions is actually figured out by a hypergeometric or binomial distributions. Both of those count the number of successes in a sample of fixed size, and the fixed size of the sample is n, the number of successes is x. The proportion of successes, denoted by p hat, in the sample is found by dividing the number of successes by the sample size. So p hat is x divided by n. Multiply both sides by n, and we get x is n times p hat. The output of the PDF then is exactly the same for proportions and for the number of successes, whether that's coming from a binomial or hypergeometric, with the different input values. So, for example, if we have a binomial distribution where n equals a sample size of 10, p or p naught is the true proportion is 0.4, it generates this PDF, this CDF, which we could get from a binomial PDF or binomial CDF on our calculators. And these are the x values, which are possibilities of number of successes in the sample going up from 0 to 10. Divide those by the sample size, we get these proportions, 0, 0.1, 0.2, and so forth. But notice the PDF and CDF values remained exactly the same. Now remember, in both cases, a hypergeometric and binomial distribution, x is going to count the number of successes in the sample. Little n is the sample size or number of trials in both cases. The difference is, in a hypergeometric, selection is performed without replacement, so probability of success is not a constant. Selection is performed with replacement in a binomial, or we can consider the population size to be infinite or so large that the probability of success is either constant or we can pretend it's constant. In a hypergeometric, n is the population size, which is finite. M is the total original number of successes in the population. So capital N for population size, capital M for number of successes in the population. Divide M by N and get P or P naught, the probability of success on the first trial, or the proportion of successes in the total population. In a binomial, you can do the same thing, but it's not going to change. The probability of success on the first trial is P naught, and it's also the probability of success on every trial, and it is the proportion of successes in the total population. Here are the basic formulas that we used before. A hypergeometric is the number of successes m. Choose the number of successes x in the sample chosen from the m successes in the population, leaving n minus m successes failures in the population, for which we're going to choose little n minus x. Multiply those two combinations, and then divide by the number of ways of choosing a sample of size little n from a population of size n. And the probability of x in a binomial is little n, choose x, p to the x, q to the n minus x, and these are both the PDF functions. The mean in the binomial is just n times p naught. It's also n times p naught, where of course p naught is big M over big M in the hypergeometric. The variance is npq. Standard deviation would be the square root of npq in the binomial. The standard deviation is, or let's say the variance in a hypergeometric is npq, but then it's times this extra factor, capital N minus little n over big N minus 1. Now the good news is all this is either built into your calculator in the case of the binomial probability or in the hypergeometric program that I wrote for this. And these allow us to compute probabilities. Once again, here's a side-by-side comparison of hypergeometric and binomial. So if we want to look at distributions of portions, we just take the p hat values, multiply them by n to get x, and then use a hypergeometric or binomial distribution to find the desired probability, or inverse functions to find the inverse probabilities. Now, let's see if we can do this. We should remember how to do this from earlier in the course. So we want to compute the following using the built-in binomial CDF to compute probabilities, or my program, inverse binomial, to program to compute inverse probabilities. The proportion of successes in the population is P equals 0.6, and the sample size is n, little n equals 15. Sampling is done with replacement, or the population is so large that we can assume that the probability of success for each element of our sample is constant or practically constant for practical purposes. The proportion of successes in the sample is p hat, and x is the number of successes in the sample. So I've given you 3 problems here, 1, 2, and 3 for probabilities, and a couple of problems for inverse probabilities. Let's see if we can work these out. Now our first step is going to be to change these things into statements about x values rather than p hat values. Let's see if you can do that first. I'm going to press, why don't you press pause, then come back when you're ready to go on. Well, hopefully you came up with this here. Basically, we just want to take this first one, multiply both sides of this inequality by n because x is n times p hat. N times p hat is x, and n times 0.1, well, n is 15, so 15 times 0.1 is 1.5. So we're looking for the probability that x is less than or equal to 1.5, but remember x has to be a whole number, so you might as well have just said probably that x is less than or equal to 1, or even if you wanted to, the probability that x is between 0 and 1, because those are the only 2 possibilities, really. The next one, when we multiply both sides by 15, which is the n, 15 p hat or n p hat is x, and 0.9 times 15 is 13.5. This time we want x greater than or equal to that, so the first one that's greater than that can actually occur is 14, so we need x greater than or equal to 14. In this case, the sample size is 15, so we're doing the probability that x is either 14 or 15 here. The next one, number 3, p hat is between 0.2 and 0.4. Multiply everything by the n, which is 15. That turns the p in the middle into an x. 0.2 times 15 is 3. 0.4 times 15 is 6. So we're talking about x is between 3 and 6 inclusive. The next one, the inverse probability, we say p hat is less than or equal to some critical value, some critical proportion value c, and we want that to be less than 0.1. Multiply by n, which is 15, and we get p hat times n is x, and then we get 15 times c. We want that to be less than 0.1, and we want to find the largest value of c, which corresponds then to the largest value of 15c, which is the largest x value. That's going to give us a probability to the left of 0.1. So we want that left tail to be small. How small? Well, not bigger than 0.1. The next one, where we want to specify that the right tail is small, so the probability of p hat is greater than c is less than 0.1. So again, multiplying by n, that's x is greater than 15c, and we want that to be small. But remember, when we do inverse probabilities, they always give us a probability to the left, and so we say x is greater than 15c. We want it to be small. Then we want x to the left of that to be large. How large? Larger than 0.9 to the left will give us smaller than 0.1 to the right. We want the smallest c value that's going to give us that. So let's focus now on the just the probability statements, and I reduced those down to the last versions we came up with on the last slide. And you should be able to use a binomial CDF to pop these 3 out pretty quickly. Let's just do them one at a time. Do the first one, press pause, and come back when you're ready. Well, all you had to do is use a binomial CDF. You tell it there's 15 trials, p is 0.6, the x value is 1, and we want the probability to the left of that. Paste that in, and you get, well, it says 2.5, and then you see e negative 5, so that's times 10 to the negative 5 times the 2.5, so that's 0.402523. If you have a TI Inspire, it works almost the same way, except the TI Inspire, you give it a lower and an upper limit here. The lower is going to be 0, the upper is going to be 1 for you guys. And the next one, let's see if you can do it. Press pause, come back when you got it. Well, in this one, we want the probability that x is greater than or equal to 14, but now if you have an Inspire, you can do that. You can just say 14 for the lower, 15 for the upper, and your binomial CDF, and it will work out just fine. But on this TI-84, anytime you have an x greater than something and you want to find a probability from you need to basically start with the 1 minus. So we do 1 minus the probability that x is less than or equal to 13. We take away 13 and down their probabilities. That leaves the probability for the items 14 and up, which is what we want. So that's just 1 minus the binomial CDF, 15.6, 13, and that's 0.005172. Finally, do the last one. Press pause. Come back. Okay, hopefully you're back now. This one, we're doing the probability between 3 and 6 on a TI Inspire. You just put 3 for the lower, 6 for the upper. Of course, 15 for the sample size and 0.6 for the probability. But on a TI-84, what you have to do is a CDF minus a CDF. So you do the CDF of the top number, 6, and then we want to subtract off the, 0, 1, and 2. So we want to subtract off up to 2. So it's a binomial CDF up to 6 minus the binomial CDF up to 2. What does that leave? That leaves 3, 4, 5, and 6 for x's, finds their probabilities, adds them up, and we get 0.094769. Now let's see if we can do these inverse probabilities. We'll use my inverse binomial program for this, inverse binom. Okay, see if you can do the first one. Press pause, come back when you're ready. Well, it's an inverse binom program. The sample size is 15. The probability of success is 0.6. And then we put in the cumulative probability, which is the probability to the left on the number 4. That's 0.1. And then it produces a little piece of the CDF table. And we look at that CDF table, and we're looking for the largest x value so that the probability to the left is less than 0.1. 7 is too big, so the largest one will be 6. That's 15c, so 6 divided by 15 is going to be our probability, which turns out to be 0.4. It's also given here in the table as well. How about the last one? Well, here it is. It's the same thing, sort of, except that this time we want, once we've made the transformation like we already did in our earlier slide, we're looking, it's the same kind of problem. So this time, though, we're wanting an x value so that it's bigger than 0.9. The first time it goes over 0.9, which, as you can see here, is 11. And the corresponding is 11/15, or approximately 0.733. Okay, let's do the same thing for a hypergeometric distribution. This time we'll be using my HGO CDF for probabilities and inverse HGO for inverse probabilities. The population size is 250. The number of successes in the population is 50. Sample size is 12. X is the number of successes in the sample, and p hat is the proportion of successes in the sample. Sampling is performed this time without replacement. So the first question is, what's the proportion of successes in the population? And then see if you can translate each of the following into statements about x. This should work very similar to what we just did with a binomial. Try it yourself this time and come back when you're ready. Press pause now. Well, the proportion of successes in the population is 50 divided by 250. That reduces to 1/5, 0.2, or 20%. We can translate each of these into statements about x by multiplying by n. N times p hat is x, and n is 12. So this 0.1 times 12 is 1.2. X less than or equal to 1.2 might as well be x less than or equal to 1, or really x between 0 and 1. P hat greater than 0.9, again multiplied by n is 12. We get x here. We get 0.9 times 12 is 10.8. X needs to be bigger than that, or equal, so it's bigger than 11, or equal to, so that's between 11 and 12. Here we multiply by everything by 12. P hat times 12 is x, and 0.2 times 12 is 2.4. 0.4 times 12 is 4.8. between there is actually really just between 3 and 4. And similarly down here, the probability that p hat's less than c is less than 0.1. We just multiply by n, and we get p hat times n is x. N times c is 12c. Where we're looking for the largest value of x, which would be 12c, that'll give us a probability less than 0.1, and then of course the largest proportion that goes with that. Similarly, p hat greater than or equal to c is less than or equal to 0.1. Multiply both sides by n, which is 12. P hat times 12 is x. 12c is here. And this less than or equal to 0.1. But we need this phrased in terms of a less than. So when we switch this to a less than, we're saying the greater to the right of this is smaller than 0.1. Then to the left of that needs to be greater than 0.9. So pulling these down to just the last statements, let's see if we can do these probabilities. They're actually pretty easy with the program. So we just run our program. We tell it the population size is 250. The number of successes is 80. 80. Did this one with 80. Sorry, instead of 50. Yeah, actually this is all done with 80. Okay, I think this has been corrected. 80 over 250 is actually 8/25, 0.32 or 32% for the proportion of successes in the population. And then this is run with 80. 12 is the sample size. Interval of successes, we go from lower from 0 to 1. And we get 0.060457. See if you can do the next one. Well, if you did this, you run the program again, still 250 for the population size, 80 for the number of successes in the population. Sample size is still 12. This time lower is 11 and upper is 12. And the probability there is 0.7 zeros and essentially an 8. Yeah, that's very, very, very small, basically 0. The next one here, from 3 to 4, we just run the same program, just lower is up is 3 and upper is 4. We get about 0.37542. All right, how about an inverse probability? The first one here says the probability to the left is less than 0.1. And we run our inverse HGO. We give it the population size is 250. Successes in the population is 80. Sample size is it's covered up there, but it's 12. And then we give it the cumulative probability, which in this case is 0.1. And it returns part of the CDF table. We want the smallest x value that goes over 0.9. So the largest x value that's still under 0.1. So that would be this one right here, which is 1 for 12c, or the x value, but the probability is the c value we're looking for, is the proportion, and that's 0.8083. There we go. Fix that. Okay, going to the next one. And this one here, again, we run our program, inverse HGO. Population size is 250, 80 in the successes in the population. Sample size is, there it is, 12. Cumulative probability is 0.9 this time, so we want 0.9. The probability to the left, we want to be bigger than 0.9. The first time it goes over 0.9, which is 6 for the x, and the corresponding p-value is 1/2. So that gives us a pretty good little review of how to use the programs that I wrote and the built-in programs in the calculator to find probabilities and inverse probabilities from distribution of proportions, where we find probabilities by either a binomial or a hypergeometric distribution.